Hello everyone, and thank you for attending this presentation. Today, I will introduce our work titled Diversity Feedback Regulated Particle Swarm Optimization with Perturbation Mechanism for 3D Lesion Shot Planning. First, let me introduce what the shot planning problem is. As shown in this illustration, gamma-ray beams coming from multiple directions pass through collimators and converge at a single point, forming a spherical high-dose region. This region is called a shot. Shot planning refers to determining appropriate shot locations so that the lesion is covered as fully as possible with an appropriate dose, while at the same time minimizing the dose delivered outside the lesion. How is the dose calculated? The dose model we use assumes that each shot generates a radial dose distribution that decays smoothly with distance, and the final dose is the linear superposition of all individual shot contributions. To evaluate a candidate plan, we use a fitness function defined as the appropriate dose inside the lesion minus the dose outside the lesion. A higher value indicates a better shot placement configuration. Now that we understand what shot planning is, we can look at why this research is necessary. That is, what motivates our work. First, let's consider the existing issues. Shot planning is an NP-hard optimization problem. The search space for possible shot placements is high-dimensional and highly irregular. When we apply a standard algorithm like PSO, it often suffers from premature convergence, meaning the swarm collapses too early and stops exploring meaningful alternatives. This loss of exploration directly limits the quality of the final plan. This brings us to our research goal. We aim to preserve search diversity so that the algorithm continues exploring promising regions, avoid premature convergence, and ultimately improve shot planning quality. To accomplish this, we propose two diversity-driven mechanisms: a diversity feedback strategy, which continuously regulates the swarm's behavior based on its diversity level, and a diversity recovery perturbation mechanism, which restores exploration when diversity becomes too low. Since diversity serves as the foundation for the mechanisms we propose, let me first explain how we evaluate diversity. In this work, we choose to measure diversity using entropy. So the natural question is, why entropy? Let's look at the alternatives. Distance-based measures, such as variance, standard deviation, or mean distance, are easily affected by outliers. Just a few particles drifting far away can create the false impression of high diversity, even when most of the swarm has already collapsed into a small region. Count-based measures, like counting how many particles fall within a certain radius, also have limitations. They depend heavily on the absolute coordinate scale, meaning that as the search region changes its size, these measures become inconsistent and unreliable across iterations. Entropy, on the other hand, offers a fundamentally different perspective. It is based on the probability distribution of particles across space. This makes it scale-independent, robust to outliers. For these reasons, entropy provides a stable and meaningful measure of swarm diversity, and it serves as an appropriate and reliable signal for regulating the behavior of our optimization algorithm. Next, let me walk you through the two mechanisms we introduce. The first mechanism is the diversity feedback strategy. Premature convergence happens when particles become overly concentrated in a very small region of the search space. When this happens, exploration almost completely disappears. Once the swarm reaches this state, it becomes extremely difficult to escape from the local optimum. To understand how diversity affects PSO behavior, let's revisit the velocity update equation. The inertia weight W determines how much momentum particles carry from their previous movements. A higher W means more exploratory behavior. Particles retain their movement and continue searching broadly. On the other hand, the cognitive and social coefficients C1 and C2 encourage particles to move toward their individual best and global best positions, which enhances exploitation. So the key idea is, when diversity is low, exploration must be strengthened. Therefore, when the diversity is low, we increase the inertia weight W, so particles regain momentum, and we decrease the cognitive and social coefficients so that particles are not overly attracted to their best-known positions. Conversely, when diversity is high and the swarm is too spread out, convergence becomes slow. In this case, we reduce W and increase C1 and C2, guiding particles to more promising regions. This dynamic adjustment follows the patterns illustrated in the plot shown in the lower left of the slide. You can see that the values of W, C1 and C2 smoothly change depending on the diversity level. This makes the algorithm self-regulating. It automatically increases exploration when necessary and strengthens exploitation when appropriate. In practice, this allows the swarm to maintain a healthy balance throughout the optimization process, preventing premature convergence while still ensuring eventual convergence toward high-quality solutions. The second mechanism is the diversity recovery perturbation. Even if we adapt the parameters based on diversity, there is a fundamental phenomenon in PSO. Because the inertia weight W is usually set below 1, particle velocities decay gradually over time. Additionally, as particles approach their personal best and global best positions, the cognitive and social terms become very small. These effects accumulate, and eventually the velocity approaches 0. This means that even if we increase W to 1 when diversity drops, the swarm may still have insufficient movement to effectively explore. The velocity simply cannot be revived by adjusting the parameters alone. To solve this, we introduce explicit perturbation into the system. However, where should perturbation be applied? If we perturb the positions of particles, the velocity update formula immediately pulls them back toward P-best and G-best, making the perturbation ineffective. If we perturb G-best, we risk damaging the best solution discovered so far, which is unacceptable in optimization. Therefore, we perturb the personal best positions, P-best. This approach shifts the individual attractors of particles slightly without altering the global best solution. Particles then begin to move toward these updated P-bests, effectively restarting exploration in a controlled manner. This mechanism is particularly useful in the late stage of optimization when the swarm is nearly stagnant. A small number of P-best perturbations is enough to reopen the search space and allow the algorithm to escape suboptimal regions. In this way, the perturbation strategy complements the feedback mechanism. Together, they form a robust system for maintaining diversity throughout the search. Now let's examine the results in more detail and understand what they tell us about the effectiveness of the proposed method. The simulation experiments were conducted on a spherical lesion with diameter 28, and we compared our method against several baseline algorithms, including Lingo, Standard PSO, and MGPSO. We evaluate the quality of each solution using 3 components: underdose, appropriate dose, and overdose. A good shot plan should keep underdose reasonably low, maximize the appropriate dose region, and minimize overdose. From the table, we can see that our method achieves the highest appropriate dose value, substantially higher than all other methods. This means the lesion is covered more completely with a clinically meaningful dose. At the same time, our overdose value is far lower than standard PSO and MG-PSO, demonstrating superior tissue sparing. Even in terms of underdose, our method performs similarly to LINGO, showing that we achieve better results without sacrificing coverage stability. To further illustrate this, the 3D visualization in the middle shows how the shots are distributed and how the dose-appropriate region is formed. The lesion area is covered smoothly, and the dose distribution is well-shaped, which indicates that the optimizer places shots intelligently rather than randomly. On the right side, the perturbation sensitivity analysis provides important insights. We tested different levels of perturbation and measured the final fitness. The results show a clear pattern. Moderate perturbation significantly improves performance by enabling the swarm to escape stagnation. This confirms that perturbation must be applied in a controlled manner. Too little fails to restore diversity. Too much destroys structure. Our design strikes the right balance, combining feedback and perturbation to maintain diversity effectively. Overall, the results show that our method effectively avoids premature convergence and delivers better optimization outcomes. Thank you for your attention. That concludes my presentation.